Hello everyone, welcome back. So today we're going to take a look at something super important, which sits at the base of the pyramid of a lot of our courses here at the school. If you ever took a course with us, you know that we deal a lot with these ideas of computer graphics, right? And one of the most fundamental ideas of computer graphics is the ability to render pixels, render triangles, render meshes, render 3D objects on the screen. And these ideas of painting these pixels on the screen, on this raster of pixels that you have on the most popular screens, is what we call rasterization. So in this video, we are going to take a look at a very popular algorithm for triangle rasterization. Actually, not just that, we are going to touch a lot of very cool ideas that are based on this important topic of triangle rasterization. And just to give you a spoiler, this video right here, we're going to take a look at rasterizing pixels on this raster on the screen, right? So triangle rasterization is one of the topics that we're going to cover. We're going to take a look at a very popular triangle rasterization algorithm that tries to take advantage of these ideas of parallel processing, right? Because GPUs usually work with parallel tasks, right? I mean, all these cores of the GPU, right? They use divide and conquer. So triangle rasterization is one of the topics. And while we are discussing triangle rasterization, we are going to talk also about some important mathematical concepts that we need to use to make this happen. For example, the cross product. We are going to use the vector cross product a lot in our explanation. So cross product is something that we're going to touch briefly. And don't worry, I'm going to try to be as beginner-friendly as possible with this topic, but you'll see, it's super fun and it's going to help us solve a lot of the problems that come with triangle rasterization. The next item that I want to cover is something called fill convention or rasterization rules. We are going to talk also about subpixel rasterization, and the next one is going to be something called barycentric coordinates, which is going to help us interpolate values inside our triangle. Kind of like what you see right here with the colors, right? The green, the red, and the blue colors, they are interpolated in the middle of the triangle. Barycentric coordinates is one technique that can help us achieve this interpolation. So these items right here are the main big areas that we're going to focus. And of course, at the end, I want to talk a little bit about optimization techniques because there is some room for improvement at the end that we can also think about. And if you're talking about software rendering or GPU rendering, then you can take different approaches into this whole triangle rasterization algorithm, right? Let me just pause for a moment and give you an introduction of why I want to talk about this. Because look, if we think about triangle rasterization, whenever we think about 3D objects, polygons, triangle, meshes, right, we have all these 3D objects that are defined by triangles, right? If we are talking about polygon rasterizers, these objects, they are formed by triangles. They have vertices, right? All these vertices of the triangles, and then we connect these triangles between the vertices. We have the edges of the triangles, and all these triangles combined, they will hopefully form something more complex, right? A 3D mesh, a 3D object that we can visualize on our screen. But the basic building blocks of these 3D objects are triangles. Triangles are formed by vertices, right? We have vertex 0, vertex 1, vertex 2. I am choosing to represent these vertices in clockwise order. Do you see? V0, V1, V2. The order that you choose to represent these vertices is super important whenever you are talking about a 3D engine. So at the beginning of a 3D engine, you need to specify what is the order, right? The winding order of the vertices. I am going to go with clockwise order because this is the order that we use in our 3D engine course at picoma.com. So I'm just going to keep consistency. Clockwise order is the one that I'm going to use in this video. It really doesn't matter, right? If you look at popular graphics APIs like OpenGL, DirectX, DirectX, I think they use counterclockwise. So it's just a matter of convention. You need to have this consistency. You start with clockwise, you continue clockwise. If you start with counterclockwise, continue counterclockwise. Right, so back to this triangle. We want to move this triangle, this perfect triangle that only exists in these mathematical terms, right? This thing right here is a perfect mathematical triangle that only exists in our minds, right? But perfect, precise triangles, they don't exist in the real world. We need to move from this mathematical conceptual triangle that only exists in our brain, and we need to rasterize, right? We need to go and create a rasterization in this discrete pixel by pixel raster that we have, which is our screen. Right? Most screen work with these ideas of having pixels. We have these pixels that we have to go analyze what are the pixels that are inside the triangle, and then we have to go and paint that frame buffer, paint that pixel at that X and Y position. So we are going to talk about a screen that has a raster, right? Rasterization has to do with this raster of pixels that we have to go and paint that pixel on or off, or even with a certain color, right? I want to paint that pixel at that X and Y position with the color red, green, blue, whatever mix of blend of colors that you want. This is the problem that we're trying to tackle and trying to solve. Rasterization of triangles. Very well. So let's go back in time, right? If you were in the 90s, in the 80s, 1990s, and if you were working with a computer that did not have a GPU, right? If we don't have a dedicated hardware, a board, and if you only have a CPU, all you have is a processor that knows how to execute instruction per instruction, one after the other, the way that we will approach this, right, and the way that we learn in our course at picomod.com is something like this. We have to go, right, the way that we started this problem was, we analyze all those three vertices, and then we have to divide this triangle in the middle, and we are going to raster and paint all the pixels from the top vertex until this middle of the triangle. And then we have a second part of the algorithm, which is from this middle until this last vertex right here. So the way that we approach this in this software rendering approach using only the CPU was, we look at that first, right, with that first vertex, and we look at the edges of the triangle, looking at the slope of that edge. We have this slope, right? So the rise over run, right? What is the slope of the edge of that triangle? Because those two slopes, the slope that goes from Z0 to V2 and the slope that goes from V0 to V1, these two slopes are going to determine how are we going to navigate that edge from the top to bottom. So we look at that slope and we calculate. We go one scan line down. We look at that slope, left and right, and we go from start to end, filling the pixels. Slope again of that edge, left and right. That slope is going to give us the start and the end, and we paint those pixels in that scan line. Right? We paint the pixels from left to right in that scan line. I think it's going to be clearer now what happens. Look at the slope again. That slope is going to give us the start pixel of that edge and the end pixel of that edge. And then we go and we raster all the pixels between the start and the end. And that continues forever, right? We look at that slope until this middle here. That slope is going to give us the start, the end, and then we fill that scan line with all the pixels. We just paint all the pixels at that row that we have. Again, slope, we're gonna find the start pixel, the end pixels, and then we just fill from left to right. Slope, start, end, fill, slope, start, end, fill, slope, start, end, fill, and you get the idea. We look at that slope, finding the start and the end, and filling each one of the scan lines. You will hear a lot of people talk about scan lines, right? Scan line rendering. This is what we are trying to do here. We are trying to fill this triangle using scan line rasterization, scan line by scan line. And this is very easy for the CPU. Well, I'm not going to say easy, but it is appropriate for the CPU because every instruction is being done linearly, right? The start, the end, and going from left to right, scan line by scan line. As we reach here, this mid part, right, as we have this half of the triangle right here, we're going to have to find different slopes. So we're going to look again at that slope now from V2 to V1. That's going to give me a different slope because we're going to have to find new start and end positions. And this slope right here, it just happens to be the same as before from V0 to V1 in this configuration of triangle. Again, going from looking at the slope, finding the start pixel, finding the end pixel, and filling this scan line right here. So this is, again, we go until the end, until we find V1. This is one of the most, it's easy to understand if you're talking about a software rendering. This is what we did in our 3D rendering course, or something similar to that, right? With a couple of optimizations here and there. This is going to give us our rasterization, our triangle. Do you see? We have that conceptual triangle before, that is in magenta, but what we end up with is this discrete, right? This raster, pixel by pixel, whatever is inside or what we consider inside a triangle is what gets to be rendered. This is usually the approach that we use if we're talking about software rendering. When I say software rendering, I mean CPU-based rendering, right? Without the use of a GPU. But what I want to talk to you right now today is, I want to show an algorithm that it is appropriate for the use of GPUs as well. Because think about CPUs and GPUs. A CPU is just usually this big important chip that knows how to execute instructions one after the other, linearly, right? When I say linearly, means that the instructions of the CPU, this instruction depends on the result of the previous one. The previous one depends on the instruction of even the previous one. So everything is sequential, linear. I cannot execute usually things in parallel with the CPU. On the other hand, the GPU is this parallel machine with several tiny cores inside, where the idea is to divide and conquer. I can execute multiple instructions at the same time with the GPU. That is why GPUs are so important, right? That's why they are so useful. They divide and conquer. We can execute things in parallel. So we're going to take a look at an algorithm that is parallel in nature. So what if we want an algorithm that can be performed in parallel, where most of the computations can be performed simultaneously? And for that, we are going to go back in time to 1988, and we're going to look at an algorithm proposed by Juan Pineda. You can take a look. It's actually super simple to understand. It's a very well-written article. You will see that this algorithm is all over the internet. It's one of the most popular implementations of this whole parallel triangle rasterization. And speaking of resources out there, I just want to make sure that we understand that we are not creating a new element here, right? This thing is a solved problem, but every programmer has a different way of tackling triangle rasterization, and you'll see several techniques out there. The main inspiration from my video was someone called Fabian Gissen, right? So Fabian is a programmer at Red Studios, and he has an excellent set of blog posts on triangle rasterization, actually the whole graphics pipeline, right? There is something called a trip through the graphics pipeline, and I learned a lot from his discussions on his blog post. You will see that we will try to follow the same implementation that Gissen did. I'll try to explain a couple of details here and there where I think it is appropriate, but the concepts and the approach that I'm going to tackle here is going to be based on Fabian's blog post, right? And also, right, there is another blog post which is based on Fabian itself from Christopher Darkhorn, and I'm going to take a little bit of this post as well because I like the approach of starting, for example, rendering one triangle and then rendering the second triangle and then looking at the problems that adding a new triangle creates. So this step-by-step approach of adding a triangle, adding a new triangle, looking at each one of these stages, this flow I really like from this blog post right here. So I'm going to take a couple of inspirations from Christopher Darkhorn as well. But keep in mind that this blog right here is largely based on this discussion that we have right here from Fabian. And Fabian's blog is largely based on Juan Pineda's article, right? The one that we just mentioned before. So let's go back to our problem statement and let's understand how we're going to approach this parallelized algorithm for triangle rasterization. And we are going to start by looking at a couple of very important primitives about our triangles and about what we are trying to accomplish. So given that we have our triangle and given that our vertices are in clockwise order, right? This is something that we decided we are going to use clockwise orientation. we're going to use C, right? So I'm going to start by declaring a couple of types and a couple of structs that are going to be important for us. So we know that we're going to have something called a vector of two components, right? So everything is going to be vectors, right? The vertices are going to be vectors with X and Y components inside. I'm calling in right now, I'm using float point numbers for now. And then we are going to have, this is super simple, a vector of vector 2's, right? So this is going to be an array of vector 2's, and for now I only have 3 vertices at these X and Y positions. This is the fundamental idea, right, that we're going to have all this new type and these vertices that is going to try to translate what we see right there, or what we are trying to imagine in our screen X and Y position. 2 things that I wanted to remember. The first thing is that the Y coordinates grows down on the screen, so you have to always consider that. Usually in mathematics, the Y grows up, but in our case, right, in computer graphics, usually Y grows downwards. And the second important thing that I want to mention is these stage that we are right here, I want you to ignore everything that happened before, right? So remember, rotating, translating, scaling the 3D object, all those things, projecting on the screen, projection, rotation, transformation, world coordinates, all those things that we did with our 3D object before, let's ignore that and let's just think that we are already in screen space, right? So we want to rasterize the triangle that was already projected on the screen. So we are not going to cover any of those transformations before, projection, anything. That is not what we want to. All we want to discuss is rasterization. So think that the triangles were already projected on the screen. They are perfectly, those are screen coordinates, right? These things that you see right here, they are just screen coordinates on the TV, right? On the screen that we want to go and then raster pixel by pixel. So this is what we want to focus, just the rasterization stage, right? So now that we have these vertices and the struct, look, I'm going to already cut to the chase and show you that. I am going to, the idea is, we are going to find a bounding box with all the candidate pixels, right? So all these candidate pixels, do you agree with me that they happen to always be in this bounding box that surrounds the triangle? So what we're trying to find is, we're going to find the x-min, the y-min, and the x-max and the y-max of that bounding box, right? That rectangular bounding box. And all I'm doing is I'm getting the minimum between the v0 x, v1x, and v2x. So I get the minimum and the maximum of all this, this bounding box, just using minimum and maximum, trying to find the minimum and maximum of all these coordinates that I have, x and y. Now that I have x-min, y-min, x-max, and y-max, this bounding box, this is the rectangular bounding box with all the candidate pixels. I am going to loop all the pixels inside the bounding box from y minimum to y maximum, and then a nested for loop that goes from x minimum until x max, one by one, discretely, pixel by pixel. I'm going to go visit that point. I'm calling it that vec2p. You see, I create a new vector2p, which is this candidate pixel, this candidate point inside the bounding box at that x and y position. And then what I want to test is that point inside the triangle, yes or no? Because if it is inside the triangle, I'm going to go and draw that pixel, right? I'm going to go and put a pixel at that x and y position with a certain color, right? Let's just say that I'm using white here. So this is it, right? It's actually super simple. We just go, we find this rectangular bounding box with all these candidate pixels. They might be outside, they might be inside. We need to go loop all these values, all these x and y pixels inside. We loop each one of the pixels, and then we test this point at this x and y position. Is it inside the triangle, yes or no? If it is inside, I go and I paint that pixel with white or whatever color you want. All good? Right, so now that we know the high-level understanding of the algorithm, breaking into the bounding box, finding if it is inside or outside, we are going to take a look at this inside or outside, if the point is inside the triangle or not. But before I do that, I just don't want this lecture to be simply theoretical. Let's see this in action, right? So what I'm going to do is, I am going to show here in my terminal, I have already a C template program that knows how to go and display pixels on the screen so we can actually see this thing in action. So if I come here to my Unix terminal, right, I am in my home folder here, I have already a project called Triangle Rasterizer because I couldn't think of anything more interesting. Right, so this Triangle Rasterizer, let me just show what we have right here. Right now we have something called a makefile, which is going to be just a file that is going to help us build and compile our source code. And we're going to look at this makefile very soon. And do you see how I have a subfolder called src? Inside src, I have a very minimal C project that knows how to display a window on the screen, and we can go and paint pixels inside that screen, right, at a certain x and y position. And do you see, I have something called display.c and display.h, which is just this source code that knows how to open a window. We're going to use SDL, right? So it knows how to open a window, creates this frame buffer of pixels on the screen, and some functions to draw pixel, right? So this put pixel at x and y position. That's pretty much what display.c and display.h have. We're going to look at them very soon. I have something called vec2.h and vec2.c, which is what you saw before, right? That definition of the type vector of two components, x and y, right, in these two dimensions. So I have this type for vec2s, and of course I have a main.c, which is going to be our main implementation, which has the main function where we're actually, everything that we're going to do is going to be inside main.c. Okay, so let me just show here quickly. Let me just go back. I'm going to use VI. You can use anything else you want. You can use Visual Studio Code. It doesn't matter, right? It's just a code editor. So VI, I'm going to open display.h, which is the header file with the API that we can use to create a window, open a window. So this is something super simple that I use, is just something called display.h with all this display, right? Monitor things to open a window, create a window. And I'm using just these standard libraries stdint and stdbool to work with integer types and Boolean types. And this is us using the third-party library called SDL. SDL is the library that knows how to create graphics on the screen, open a window, manipulate keyboard input, mouse input. So we are using the SDL library just so we can display things on the screen. I have a couple of constants here. I am declaring screen width and screen height 128. And look, I'm going to keep this resolution super low because I want us to really see the pixels, right? I want to actually see the little square by square row, all this rasterizer in action. Because if we just use this super high resolution that we have in our monitors, it's very easy to get overwhelmed and not really see what's going on pixel by pixel, right? So by using this 128 by 128, we can actually see what's going on. It's a lot more discrete. We can see the discreteness of the pixels. And it's kind of like those Pico 8 resolutions, right? So I think it's going to be super cool for us to see things in this very low resolution scenario right here. Right, so 128 by 128, this is the resolution that we have. This is just declaring the frames per second by 30, and then a couple of other constants. And then I have a function to create a window, a function to destroy a window, right? I have a function that's called fixed frame rate, just to make sure that we keep that 30 frames per second constant, right? That fixed 30 frames per second. And then I have something called clear frame buffer. So I can clear the entire frame buffer with a certain color. And just to make sure that we understand what we're talking about. Frame buffer is a super important concept, which is this raster, right? So a frame buffer is this mirror in memory of what we're going to display on the monitor. So it's basically this big array of color values that we can go at that X and Y position and paint with a certain color. So I can clear the color buffer. I can also actually render the frame buffer, right? So this frame buffer is what we have in memory. I can clear, and then at the end, after I am done manipulating and painting the pixels, I ask to render the frame buffer, and it goes and displays, right? And goes and shows this back buffer as the front buffer to actually display on the monitor. And this is our only important function that we have, is called drop pixel at a certain X and Y position. Do you see how I'm using unsigned integer of 8 bits? I'm just keeping things very, very short here, very, very low, right? 8 bits for X and Y. And I have an unsigned integer 32 bits color, right? The colors that we're going to use, they are going to be 32 bits. So I have 32 bits. I can select the alpha, the red, the green, and the blue. This is how we can manipulate R, G, and B of what is the red, green, and blue that we're going to paint on the screen. So this is the API of this display.h. This is all we really have to use. We can also use, let's say, the vec2, right? So vec2.h, I have a vector2 file that is super, super simple, as you can see right here. My vec2 is basically just a struct with X and Y. I'm calling it vec2, right? So it's a new type that I'm defining called vec2 underscore t, and this underscore t is super classic in the C programming, is a new type, right? So whenever we have a new type, I say underscore t. Vec2 new, to create a new vec2 passing an X and Y position as parameter. I can add two vector 2s, I can subtract vector 2s, multiply, divide. This should be familiar to most of you, right? It's just basic vector math. I can take the length, the dot product, the cross product between two vectors, and I can normalize. That's it. You see, not much going on, just a very, very, very basic vector 2 implementation. If you want to take a look at how display.c is implemented, you can actually come to display.c and look at the implementation of those functions, that API that I showed before. This is how you create a window. So you use SDL, you can create a window, create a frame buffer. This is how you draw a pixel at that X and Y position. You just go at the frame buffer and you set it with that color. So I'm not going to show the implementation that much. It's super, super simple. It's just creating a window, destroying a window, setting a pixel on the frame buffer, displaying the frame buffer. This is what we have in display. And if you really want to look at what we have in vec2.c, you can also look at the implementation of new, add, subtract, multiply. Super, super simple stuff. I'm not using any fancy SIMD, anything, just super simple software-based vector math, right? Because what we really want is our main.c. So let's edit main.c and look at what we have. Right, so super simple again. Couple of standard libraries, stdio, stdintegers, boolean, sdl.h, and then I am including, of course, the display.h and the vec2.h with all those functions that we can call to create a window, destroy a window, draw the pixel at a certain X and Y position, use vec2s all over, so that's it. Super important also, in C, we don't have a standard minimum and maximum function that we can just include. So I am just defining this macro here, you see, define something called min between A and B, which is basically if A is less than B, then I return A, otherwise I return B, and the same thing, I'm defining a maximum macro, that is, if A is greater than B, then I return A, otherwise I return B. So this is basically me implementing really quickly the minimum and maximum functions between A and B numbers, right? Because we are going to use that minimum and maximum to find the bounding box, remember, between the x's and y's of the triangle. I have something, a boolean called isRunning, that I start with false. I have my vertices, remember that we saw x and y positions at these screen coordinates, right? These are screen coordinates. They were already translated, rotated, transformed, they were projected. These are just screen raw coordinates that we're going to start rasterizing our triangle for the vertices v0, v1, and v2. Right, I have something called process input that knows how to look at the keys, right? So if I press escape, I just set isRunning to false. So this is just basically boilerplate, so we can open a window, close a window, and do all these things. Let me just skip this triangle fill, skip the render. Let's just look at the main function, because this is the main function, right, after all. So as we start our program, we start creating a window, and then we return true or false to see if it's running. And then I have my game loop, right, the classic game loop. So while it's running, I am fixing my frame rate just to keep those 30 frames per second. I process input and I render my scene. This happens frame per frame, right? So this is our game loop, frame per frame, hopefully 30 frames per second. And then at the end, we destroy the window and we return to the operating system saying, look, return exit success, return 0, everything worked out fine. But the most important thing is, we looked at process input and we have the render function that happens to render frame per frame. What do we do at the render function? I clear my frame buffer with the color FF, so it's full alpha, right? So no transparency, 0, 0, 0, 0, 0, 0. So 0, 0, blue, 0, 0, green, 0, 0, red. This is the blue, green, red order that I have, right? So we are using this RGB format, and also, since it is 32 bits, we have this first alpha right here, which is going to usually be full, right? FF, opaque, no transparency. I am creating 3 variables called v0, v1, and v2 that are based on that array, vertices at index 0, 1, and 2. So I have v0, v1, and v2, and I have a function called triangle fill, which is going to be the function responsible for going and rasterizing the pixels inside the triangle from this triangle that has vertices v0, v1, and v2 using this color. I am using the color full alpha, no blue, full green, no red. So it's going to be a green triangle on the screen. And at the end, I render my frame buffer after I'm done drawing everything. This is happening frame per frame, right? So our attention should be focused on this function right here called triangle fill. This is what we want to implement to actually go and implement that Juan Pineda algorithm. So this triangle fill, I receive 3 vector 2s, V0, V1, and V2, and a 32-bit color, right, this RGB color. I find the bounding box with all those candidate pixels, exactly what we did before and we saw on the slides. So I have an x min, y min, x max, and y max, this bounding box coordinates. And do you see how I'm using that macro? I take the minimum of the minimum between V0, x, and V1, and then I use the result with the minimum of V2. So this gets the minimum between V0, V1, and V2, the minimum between V0, V1, and V2 y coordinates, and the maximum of the maximum and the maximum. So I get the minimum and the maximum of this bounding box with all these candidate pixels that might be inside and might be outside the triangle. And then I have to loop all the candidate pixels. I loop all the rows first, and for all the rows, all the columns, all the x values, I create this point P, vector 2, from this x and y position that I am currently visiting, and we have an important to-do. Are we inside or are we outside the triangle? This is what we have to discuss, right? So how do we define if a vector, a point, is inside or outside the triangle? And if it is, I draw my pixel at that coordinate x and y. Just to show this working, let me just ignore this if statement and let me just draw that pixel anyway, right? So let's just always draw a pixel at that bounding box that we have. How do we compile and build our program? Well, if you look at Makefile, I have 3 rules here, right? I have a build rule, I have a run rule, and I have a clean rule. This is what we're going to use. We're going to use GCC as our main compiler. GCC, I want to compile everything inside the source folder that ends with a .c, so everything .c. This is required for SDL to work. We need to go and set some flags for SDL to work. So this is how we set the flags for SDL to be compiled and linked. I am also linking with the math library, right? So the math.h, so linking with the math library. And what is the output executable that I want, the object file? I'm calling it rasterizer. Again, I wasn't very creative with my name. This is the build rule. This is how we build our program. This is the build command using GCC. I have also something called run that just goes and say /rasterizer to execute my executable, and clean just goes and removes that executable from the folder. Again, you don't have to do that, but that's something that I like doing. So instead of typing always GCC, star.c, etc., I can come here and say make build, and that will execute from the Makefile our build command, right? Since make build is the first rule, I can also say just make, and that will execute the build rule. So do you see? GCC, source, star.c, SDL, flags, LM, rasterizer. There was no output, right? And usually no output for Unix is good news, because if you look right here now, we probably have a new file called rasterizer, and that is an executable file, as you can see there. I can execute this thing saying /rasterizer, or as you saw, we can just say make run, which is going to execute that rule. Look at that. We have a bounding box, right? So we are painting all the pixels inside the bounding box, regardless of if they are inside or outside the triangle. This is exactly what I expected to see. And we are seeing our green color because that's the color that we used. Right, so if I press escape, we are back to our Unix terminal. Perfect, so we have a boilerplate. All we need to learn right now to rasterize that triangle is to define if a point is inside or outside a triangle. And this is what we're going to see right now. Right, so this is the problem statement that we have. Given that we have vertex V0, V1, and V2, and we have a point P, right? You have to remember that this point P is going to be all the points in the bounding box. But let's just say that we have this point P right here. How do we define if a point P is inside or outside a triangle? Well, one thing that you will see is we usually look at the triangle by vertices, but also the edges of the triangle, right? So we have all these different edges of the triangle. If I have a point P, the edges, since we are looking at this clockwise orientation, I have an edge that goes from V0 to V1. This is the edge, right? So do you see how this edge is a vector? I go from V0 to V1, I have another edge that goes from V1 to V2, and another edge that goes from V2 back to V0. These are all the three edges, the three vector edges of my triangle. Given that I have these three vector edges and I have a point P, I can start thinking about that as vector math, right? Because everything is vector. The vertices are vectors, the edges are vectors, and even point P is a vector. So look, the way that people decided to approach these ideas of if it is inside or outside the triangle, do you agree that if I look at my point P, and if I look at all the edges, and if I have this clockwise orientation of the vertices and edges, my point P is inside the triangle if point P is to the right of all the edges? So if I look at point P, it has to be to the right of this edge right here. You have to just twist, right? You have to just switch your head and think that our edge is this one pointing right here. So it has to be to the right of that edge, right? It is to the right. And also, it has to be to the right of this edge right here between V1 and V2. It is to be to the right of this edge and also to the right of that edge, right? So it has to be to the right of the edge. If these three things are true, if it is to the right of this edge, to the right of this edge, and to the right of this edge, V2, V0, if all these three things are true, our point P is inside the triangle. So this is the rule. If point P is to the right of all three vectors of our triangle, then P is inside that triangle. And on the other hand, let's say if P is to the right of the first edge, to the right of the second edge, but it is to the left of the third edge, that condition is broken, our point P is outside the triangle. So again, just as a summary, if our point P is to the left of at least one of those vector edges, then P is outside our triangle. Very well. So I want to talk to you about these ideas of inside and outside and left and right, because our problem became, instead of thinking about if a point is inside or outside a triangle, now it is a point to the right or to the left of a vector edge? Right, so this is our mathematical problem now. How do we define if a certain point is to the right or to the left of a vector edge? And I'm going to start by looking at something super important that we're going to use a lot in this video, and we use a lot all over the place, right? If you ever took a course with me, vector math is, look, it's at the base of the pyramid of all our courses, right? If you're talking about 3D graphics, physics simulation, all those really cool things that we do with computers and games and game development and vector math is always there. And to answer this, to give us a result of what is to the right and what is to the left of a certain vector, we're going to look at a very important property of a vector operation called the 3D vector cross product. Because the cross product can help us define if something is to the right or to the left of a certain vector, right? So let me just start by saying that whenever we study about cross product is usually only defined in 3 dimensions. So what I'm going to explain right now, it is true for 3D vectors, but I'm going to explain later how we can also think about that using 2D vectors, which is what we're going to use in our screen space, right? So cross product for 3D vectors is, given that we have any two vectors, the cross product between vector A and vector B is always going to result in a new vector that is perpendicular, that makes an angle of 90 degrees with both A and B. So we are going to have a new vector that is always perpendicular, makes an angle of 90 degrees with these other original vectors A and B. That is the A cross B. You see that green line arrow there? That is the new vector, that is the cross product vector. And this is going to help us with these ideas of how do we determine if something is to the right or to the left? Because depending if B is to the left or to the right of A, that cross product is going to change its size and magnitude. It's going to become positive or negative, right? If you go back in high school books and stuff, you're going to see that the vector cross product is defined and is given by these formulas right here. So I am calling the cross product here n because, look, n is for normal. Do you agree that that arrow right there is the normal vector of this plane right here that makes an angle, right? It's perpendicular to this plane formed by A and B. So you will see people call about this normal vector is given by the cross product, right, between A and B. So to find this new 3D vector, we have to find the x component, the y component, and the z component of that perpendicular cross product vector. And the x comes from the y of A times the b of z, right, the z of b, minus az by. The y comes from az bx minus ax bz, and the z component of the cross product is the cross between the other two, right, ax by minus ay bx. You don't have to really memorize this, just remember that this is how, remember in high school we had to go and compute the cross product. This is what we used. You can go derive these things. I won't derive this cross product right now because all we are really interested in is the fact that we have that perpendicular vector, which is, in our case, I'm calling it the normal vector. This is the cross product, and this is how we get the x, the y, and the z component of the cross product. Right. Knowing that the cross product gives us a perpendicular vector, we have something else that we have to consider, right? Because the magnitude of the vector cross product is related to the angle between vectors A and B. Right, so there's a lot here that we have to unpack. The magnitude, so the size, the length, when I say magnitude of a vector, is the length of a vector. So the length of that vector cross product has everything to do with the angle between vectors, the original vectors A and B. So that angle that I'm calling theta here, right? So the angle theta is going to be. This is how we find the magnitude, the length of that cross product, right? The length is the length of A times the length of B times the sine of that angle. So that angle, as it increases, the sign changes, right? So we're going to have, as A and B are changing directions, the angle of these things are changing. The length of that vector cross product has everything to do with the angle between A and B. And I want to show here a quick animation, so pay attention to this image right here. Look at vectors A and B. Look at what happens as B changes the angle around vector A. So as we rotate and as we increase the angle of that second vector, look at what happens to the cross product, that perpendicular vector. As we rotate to the left, it grows, and as it goes to the right, it becomes negative. So do you see? The length is positive or negative, depending if the vector B is to the left or to the right of the vector A. This is extremely important for us to understand. Do you see? We have the magnitude of the cross product vector. It has everything to do with the angle between A and B. If that angle is to the left, we're going to have a positive cross product between A and B. But if that B vector goes to the right, the cross product becomes negative. And this is also why, if we just come back here, you will see mathematicians say that the cross product is not commutative, because this cross product can be there or this way, depending if it is A cross B or B cross A. You see, if it is to the left or to the right, cross product is not commutative. A cross B is different than B cross A. And this has everything to do with this to the right or to the left of the vectors that we are taking the cross product, right? Cross product is not commutative. The order of the vectors of the cross product matter in the result, and this order has everything to do with our answer. Because if something is to the right or to the left, our cross product is going to be positive or negative. And this positive or negative result of the cross product is what is going to give us the answer. Is something to the right or to the left of that edge of that triangle that we're trying to find? All good? So this is super interesting, right? The fact that we're going to use vector math to answer these ideas if something is to the right or to the left. But we need to quickly stop here and think about something. In the case of our triangle edges and the point P, what are the two vectors that we have to take the cross product between? We do have two vectors here. We have this vector that goes from v0 until v1, this is our edge, and we have this other vector that can be getting from v0 until p. So if I take the cross product between these two vectors in the correct order, and if the cross product is positive or negative, I know if this p is to the right or to the left of this edge right here. And the other way as well, right? So now I have to go to this next one. I have this edge and this vector from the first vertex until P. Take the cross product in the correct order. It is to the right or to the left if it is positive or negative. Same thing with the last one. From V0, from V2 to V0, I have the edge, and then from the first to P, I have that thing. If it is positive or negative, to the right or to the left. This is how I know if things are to the right or to the left. I have these two vectors always, and then I take the cross product in the correct order, positive or negative, to the right or to the left, turning, right? Good stuff. Right, so another problem is, okay, Gustavo, you just told us that cross product really is only defined in 3 dimensions. So why are you talking about cross product in 2D? What are we talking about here? Right, I want you to think about this. Cross product, yes, it is only defined mathematically in 3 dimensions, actually 3 dimensions and 7 dimensions, but I don't want to go their way. So 3D and 7D, 3D is really how we define cross product because it only makes sense to have a perpendicular vector in 3D. But the way that programmers kind of cheat the cross product in 2D is we think about the cross product in 2D as this arrow pointing perpendicular to the screen. Right, so you have to imagine that there is this imaginary vector that is perpendicular to these 2D vectors on the screen. And this 2D cross product that you see right here, programmers will call the cross product in 2D as the value of the magnitude of the z component of that perpendicular imaginary vector that is shooting through the screen. So it is going to be shooting positive or negative outside or inside the monitor, and depending on that value, that z component of that imaginary vector, then we know if that z component is positive or negative. That is what we call the cross product in 2D. And if you remember, the z component of the cross product is ax by minus ay bx. Is the cross between the x's and y's minus y's and x's. It's almost like the determinant of that matrix, right? So I just go and I cross minus cross, x's and y's. That is going to give us the z component of that imaginary vector that is perpendicular to these 2D vectors on the screen. So this thing right here is what we call the 2D cross product, and this is what we're going to use in our source code to determine if the cross product is to the right or to the left of our triangle edge. So if we come back here, you see that we have all those 3 scenarios, right? We have the point P, and then we have all these 3 edges with these 3 vectors. We have to make sure that the cross product between V1, V2, and P is greater than 0. The cross product between V0, V1 edge and the point P is greater than 0, right? The 2D cross product that we just saw, the little hack, and the cross product between V2, V0 and point P is greater than 0. If all this is true, and this is true, and this is also true, these 3 things need to be true. If this is satisfied, we have point P inside the triangle. We can go and we can paint that pixel with the color that we want. This is it, right? So let's just go ahead and look at our source code. If we edit main.c, if we look for triangle fill, yeah, so this function right here, we are going to have to compute those 3 cross product between the point and the edge. We're going to have 3 cross product values, right? Because we have 3 edges between those edges and the point. So I'm going to call this W0, and you will see that W, right, for this cross product right here is very customary in the bibliography for this particular problem. So W0 is going to be, I'm going to call, let's say, the edge cross. Let's create a function called edge cross between the vertices and the point, right? So let's say between V1 and V2 and point P, and we're going to have, let's just define here this function. It's going to be an integer edge cross between vector 2, let's pass as reference, right? So I pass a pointer to the first vector, let's just call it A, a pointer to the second vector B, and a pointer to our point P. And you know what? Let me just save us some time, and I'm going to paste here the body of this function. So things that we should pay attention here. The result of this function is, for now, an integer value, because do you agree that we are only visiting integer pixel values for this point P? Everything is integer so far, right? So integer from x minimum, y maximum, x maximum, y minimum, everything in this bounding box is just pixel by pixel. We are going discretely pixel by pixel. So the edge cross is actually going to be, in this case, since we are only dealing with integer values, is going to be an integer value as well. And in line 52, since I'm passing these pointers, I need to pass a reference to v1, reference to v2, and reference to p. Right? Just passing things as pointers to our parameters. Right, so what do we do with a, b, and p? First, I am getting a new vector 2, which is the vector from a to b. This is going to be v0 to v1, or v1 to v2, or v2 back to 0. So this is the first vector to the second vector. This is our edge, correct? So ab is our edge. I get that by subtracting bx minus ax and by minus ay. This is our edge. And I also have that vector that goes from the first vertex to the point P, which is px minus ax, py minus ay. And remember, this is the cross product that we just saw before. This is the magnitude of the z component of that imaginary perpendicular vector that is going outside the screen. It is the cross between abx times apy minus aby times apx. Just cross minus cross. This is how we get the cross product between the edge and the point. Super. Now that we have this function and we have this edge right here, this is w0, the first cross product. Let me just yank and paste. I'm going to have w1 and w2, which is going to come from the other vertices with point P. So this one is going to be between v2 back to 0, so replace 2 and v0, and this one is the last one, which is from v0 and v1. Right now, it really doesn't matter the order, as long as you keep the consistency and it is clockwise, it should be okay, right? If it is v0, v1, v1, v2, right now it doesn't matter as long as you get the correct edges one after the other. So now we have w0, w1, and w2. What is our condition to see if the triangle is inside, if the point is inside the triangle? Well, it is inside if w0 is greater or equal than 0, and w1 is greater or equal than 0, and w2. If these three things are true, it means that we are inside. So if we are inside, if that thing was true, I go and I draw my pixel at that position. Right. Moment of the truth. Great, no errors. Is our implementation correct? Look at that. That is beautiful news. So we have screen coordinates, right? This point right here, this is v0, this is v1, and this is v2. Pixel by pixel, we tested the point at that pixel, at these integer coordinates, one by one to check with the cross product with the edges to see if they are inside or not. Only the pixels that are inside the edges are being displayed. This is great news. So we should be able to come here and start adding new vertices to our system so we can have new triangles. So instead of having, let's say, 3, let's just add 2 more. So now I have vertices 0, 1, 2, 3, and 4. And all I have to do is, let's go down, and I want to start adding them and asking to fill these new triangles, these new triangle faces that we have. So I have now vertex 3 and vertex 4. And besides having this triangle face from v0 to v1 to v2, I can have a new triangle fill from, let's see, it has to be clockwise, right? So v3 to v2 back to v1, which is our second vertex. And let's put a different color here. So let's add this color, and we should be able to have one more triangle, which goes from, this is going to be at the top. So this goes from V4 onto the second one, back to the first one. And let's just change this color. Let's use this RGB code right here. So if we save, compile, and if we run, would you look at that? Now we have 3 triangles. We have the first one, we have the second one right here, and this top one that goes from this vertex to this vertex to this vertex, right? All of them in clockwise order. And this looks pretty cool, right? We have these different triangles, but I need to talk to you about a very subtle thing that happens whenever we are rendering these things, because do you see how all these triangles, they share an edge? This edge right here goes from V0 to V1, and the bottom part of this triangle also goes from V1 back to V0. So these triangles, they are kind of glued together, right? They are sharing that edge. And this also happens right here. This triangle, green, and the pink one, they share this edge right here. And I am going to do some fancy video editing here so you can see what happens. Because I don't know if you noticed or not, but we have a very small issue here. So I'm going to toggle the image of all these triangles on or off to see if you spot what we are talking about. Look at that orange triangle as I disable and I enable. Do you see how we have an overlap there? Actually, it's an overdraw, right? It's even worse. We are drawing twice these pixels right here. So these pixels from this edge are being overdrawn by these ones. Correct? So we do have an overdraw there. And that also happens with this edge right here. Look at what happens as I hide that green triangle. Do you see how we have this overdraw right here? This green triangle is being drawn on top of that pink one. So all these pixels, we have that overdraw right here. And this is visible because we have this very low resolution, right? But if you have this 4K monitor with a really high resolution, it will be quite difficult to actually spot this overdraw right here, but it is there. So whenever we have the situation where you have all these pixels from this edge and this edge, where there is this tie, right? These pixels, they are tied between one triangle and the other. We need to come up with a convention, a rule, that determines which pixel belongs to which triangle, right? We need to have a rule that breaks that tie. And this is exactly what I want to discuss right now, because we have to discuss these concepts of fill convention or rasterization rules. So what I'm calling fill convention here, or you will see the bibliography call this also rasterization rules. And if you look at something like DirectX or Direct3D, they actually have these rules documented, right? The rasterization rules. What happens when you have these triangles that share an edge? Well, some of these graphics APIs, they define a special rule. So for example, the DirectX, they have something called the top left rule, which I'm going to explain right now, right? They define what that means, when does a pixel belong to one triangle and the other. You can actually come here and read what they have, but I'm going to try to simplify things. So if we talk about fill convention, right, these conventions on how we fill the triangles of our system, one very common approach and one very common rule is what we call the top left rule. And you will see that most graphics APIs out there, they actually implement this top left rule. And in a nutshell, the top left rule tells us that a pixel center is defined to lie inside of a triangle if it lies on a flat top edge or a left edge of that triangle. So if we are talking about the edges of the triangle, a pixel will be considered inside the triangle if it is on a perfectly flat top edge or a left edge of the triangle. And this is quite of a mouthful sentence, so let me just look at some examples of different configurations of triangles so we can identify what am I talking about, what is a left edge, what is a flat top edge. Let's look at that first triangle right there. So the first one on the far left, do you agree that we have one left edge, which is that one right there? That is what I'm talking about when I say a left edge. The second triangle also has a left edge, but also has something which is a perfectly flat top edge, where all the pixels of this top edge right here, they lie on the same vertical value, right? So this one has both a flat top edge and also a left edge. This triangle right here, what do you think? Does it have a left edge? Yes, it does. This is a left edge, right? So this is also a left edge. Does it have a flat top? No, it does not. And this one right here on the far right, what do you think? Well, we know that it doesn't have a flat top, but does it have a left edge? Yes, and it actually has two left edges. So you see, it has the left edge that goes from the bottom to the middle, and then the other left back to the top vertex. And the way that this works is, since we are defining that if we are on a flat top or a left edge, the pixel belongs to that triangle, it means that the pixels that are here on this right one, they should not be painted, right? So if I am exactly in this right edge right here, this edge should not be on this triangle. And this right one should not be painted on this triangle. Right? And we are looking at just two triangles right here, but this is going to become super complex because we have, if you look at a 3D object, there are so many triangles sharing edges, right? And we need to think about this quality of the image, about overdrawn or even gaps on the triangles. What is inside which triangle, right? So which pixels belong to each triangle? Rasterization rules. You are removing the edge of some triangles, but those pixels are going to be available for a potential next triangle that is going to be beside that one that you just removed, right? I think you get the idea. You are removing some of the edges of some triangles, but then those edges that you remove from this triangle are going to be part of a different triangle that is to the side of that one, right? So that is the whole reason why we have this convention, this rule. And look, it's very easy for the human eye to go and spot what is a flat top, what is edge, but we need to come up with a mathematical rule. How do I identify what is a flat top and how do I identify what is a left edge on this triangle? So I'm going to leave these triangle configurations up there so it's easy for us to understand what's going on. And I'm going to show here, the algorithm is very simple. You will see, let's say that we have an edge that has a start and an end, right? And this can be right now from V0 to V1, V1 to V2, V2 back to V0 to V3. So depending on what is the edge that we're talking about, we're going to have a start and an end vertex, right? And then we have this vector, right? Do you understand that we have these vectors, right? All the edges are vectors from one vertex to another vertex. So this code right here is going to be a Boolean function, is top or left, that receives a pointer to a vertex start and a vertex end. I am finding the edge between that start and that end, which is basically a subtraction, right? The end x minus the start x and the end y minus the start y. Just vector subtraction will give me this vector from start to end. And then the question is, how do I know if this edge is a flat top edge? And how do I know if this edge is a left edge? Because I have to return true if it is top or if it is left. So let's just think of the easiest one, right? So this idea of, is it a flat top edge, yes or no? So do you agree that a flat top edge, the one like that one that you see there, the second one, to be a perfectly flat top edge, all the y values of the pixels and the y values from the start to the end, they need to be exactly the same. So the edge y needs to be 0, right? So perfectly 0. This is how I identify if we are on this top edge, but also the edge x needs to be greater than 0, so needs to be positive, pointing to the right in this clockwise configuration that we have, right? We have all this clockwise configuration. It needs to have an x pointing to the right. This is how we identify if this edge is a flat top edge. If the y's are exactly 0 and the edge x is pointing to the right, then it is a perfectly flat top edge. How do we know if it is a left edge? Well, think about this. If we're talking about a clockwise orientation, all the edges that are left, they will be pointing up. So the y component of that vector is always negative. So if the edge dot y, right, this edge that goes from start to end, if the y is negative, if it's less than 0, that thing is pointing up. So that is true for that first triangle right there. Do you see? The y is negative, pointing up. That is true to the second one. This one is pointing to the right, but the y is negative, pointing up. And this one, y points up again, right? Negative. So everything that has this y pointing up on the screen, it is a left edge. Then it's just a matter of returning. Is top edge or is left edge? This thing right here, you will see that it's super easy for us to identify. And if we come back here to our code, a little before our fill function, let's say before the edge cross function that we have, I can just paste that code. So now we have a function that knows how to identify if an edge is left or top. Because look at what we are going to do. Right here, actually before the for loops that are going to visit pixel per pixel, I'm going to create something called a bias factor. And you will understand very soon what this is. So this bias 0 is, I'm going to test, is top or left edge. What is the start and what is the end? So this one goes from V1 to V2. So V1 to V2. If this edge that goes from V1 to V2 is either flat top or left, I'm going to have a bias factor of 0. Otherwise, the bias factor is -1. And I'm going to have a different bias for each one of the edges. So now I'm going to have a bias 1 and a bias 2. And the bias 1 goes from V2 back to V0. And the bias 2 goes from V0 to V1. And why am I creating this bias factor 0 or -1? Because I am going to come here and I'm going to take the value of that cross product of that edge function that we had, and I'm always going to add the bias at the end. So W0 gets incremented by 0 or -1, W1 gets incremented by 0 or -1, and W2 gets incremented by 0 or -1. I got this technique right here from Fabian Gissen's article on triangle rasterization. The idea here is that I want to compute this bias just once per triangle, right? I don't want to compute this bias every pixel. And here is the catch. At the moment that I add either 0 or -1 to this cross product value, this edge function, this W0, W1, and W2, this test, if it is inside or not, I'm going to go and push to this negative domain, right? So if I'm going to go and always add -1, since we are always talking about integer coordinates for now, this is okay, right? -1 is the value that you have to go and push everything that is on that edge to go to this negative domain and then doesn't get displayed. So we are basically pushing everything else -1, but if it is a top or left edge, we add 0. So everything gets squeezed, pushed almost to the center of the triangle. So by pushing things that are not top or left to the center of the triangle, I go and I push everything and I basically remove that right edge that I had potential, right? So I squeeze everything to the center of the triangle, but if it is a top or a left edge, I have 0, so I do not do anything, right? This is the logic that Fabian is trying to tell us whenever we are adding this bias factor every time. And super important, as soon as I add -1, this test right here becomes false and we do not draw our pixel. We are not inside this triangle, but we might potentially be inside a different triangle in the future that might share an edge with this one. Got it? So I think this is enough for us to test if our triangles are still overlapping. Right, so I don't think we can actually see the difference, but if I toggle visibility between the triangles, look at that triangle at the top. No overlap, right? And look at that beauty. No overlap between the triangles. And even better, let me just toggle between fill convention and no fill convention, right? Fill rule and no fill rule for us to see the difference of the triangles being rendered. So fill convention, no fill convention. Fill convention, no rasterization rule. Rule, no rule. Do you see how we are basically removing those pixels on the right edges and also that flat bottom part? Depending on what we remove from some triangles, those triangles get displayed on the next triangle, right? So whenever we remove something from a triangle, it becomes available for the next triangle that is sharing that edge. So no rasterization rule, rasterization rules. And no overlap, and that is beautiful, beautiful news. Do you see? As simple as defining a bias factor once per triangle is enough for us to go and nudge that value to either negative or positive to define if we are inside or outside the triangle, right? This is happening edge per edge. So this is the first edge that goes from V1 to V2, second edge that goes from V2 back to V0, and that third edge that goes from V0 to V1. Each edge has its own bias factor, either -1 or 0 if we have to display those pixels on the edge or not. And remember that this offset of -1 is super easy so far because we are only talking about integer pixel coordinates always, right? Our vertices are always snapping to the raster grid. There is no floating point values. Everything is integer pixel based. So that is why it was so easy for us to just add this -1 and then push those things that were in the edge outside negative, not displaying those pixels. Remember, it's almost like we are squeezing everything to the center of the triangle whenever we are changing this cross product value right here. Good stuff? So right, I want to talk to you about evolving our rasterizer because right now we only have this solid color per triangle face. I don't want to have only this flat shading option. I want to have potentially interpolation of values between vertices, right? So what if I want to have a different color value here internally on this triangle, pixel per pixel? And this has everything to do with us interpolating these values, right? We're going to interpolate the values between vertex 0, vertex 1, and vertex 2, and then find a different color, a blend of, let's say, different colors or different values per pixel inside our triangle. And this has everything to do with this next topic of interpolating values between vertices. So the question is, what if I want to interpolate values inside the pixels of the triangle? Because if we are visiting pixel by pixel of our triangle, right, all the rows and all the columns, I should be able to go and find an interpolation between values of V0, V1, and V2. For example, let's say that at V0 I have one color, V1 I have another color, and V2 I have another color. Let's say red, green, and blue. What if I want to interpolate these values and find what is the color that I should paint right here? How do I blend those colors and interpolate them to find this smooth interpolation of colors for each one of the pixels? That is one application. Let's say, super important, if you ever studied computer graphics and 3D modeling, what if I want to do some texture mapping, right? So what if I have a UV coordinate of the texture for V0, and I have a different UV coordinate of the texture that is mapped to V1, and a different UV coordinate of the texture that is mapped to V2. I should be able to go and interpolate these UV coordinate values to find what is the UV coordinate interpolated that I should go and then pick the texel color of the texture to paint this thing, mapping that texture in this triangle. You see? Interpolation of values. And one of the most popular approaches that we used to do back in the day, and I still like using, is basically linear interpolation, right? I can just go and do some linear interpolation between V0, V1, V2 together and get that interpolated value with these different weights, and I will find an interpolation right here. But you will see that GPUs and graphics APIs, they like to use something different, which is actually super cool, which is called barycentric coordinates. And the name is super scary, but it's actually a super simple idea. Barycentric coordinates is going to be a coordinate system that is going to give us the position of this point P based on the vertices of the triangle. Right? So barycentric coordinates is a set of coordinate values that has everything to do with where this point P is in relation to the other vertices. So it's almost like weights. How much is this point P? How much am I pulling to vertex 2? How much am I pulling to vertex 1? How much am I pulling to vertex 0? Barycentric coordinates are going to be a set of 3 values, right? So barycentric coordinates are going to be 3 values, alpha, beta, and gamma, and you will see books call these things different things. I like to call them alpha, beta, and gamma. is almost like percentages of weight, right? So what is the percentage that alpha is pulling, right? Alpha is the percentage that is pulling to V0. So how much am I close to V0? Beta is how much am I pulling V1? And gamma is how much I'm pulling to V2. So alpha, beta, and gamma, they are going to be numbers. They are almost going to be percentages because alpha plus beta plus gamma is always going to be 1.0. Right? The addition of alpha, beta, and gamma is always going to give 1.0, and this is what is the percentage of this pulling V1, what is the percentage pulling V0, and what is percentage pulling V2. These are barycentric coordinates. Barycentric coordinates are 3 values that represent where that point P is inside the triangle. So we are going to find the alpha, the beta, and the gamma to represent where that point is right here. Why is it important for us to find alpha, beta, and gamma? Because these alpha, beta, and gamma, they are going to be weight factors. They're going to pull and push that P value. I can use these values as interpolation weights. So this is in vector format. I have my point P, my vector P, comes from the alpha weight multiplied by V0 plus the beta weight multiplied V1 plus the gamma weight multiplied V2. Do you see how I'm talking about weight factors? Multiplying alpha weight by V0 plus beta weight factor by V1 plus gamma weight factor by V2. This is us interpolating the values to find this value of the P right here, right? Whatever I want interpolated for P. So this value V0 could be a color of V0. This can be a color of V1 and a color of V2. If I multiply the weight alpha by the first varying, the beta by the second varying, and the gamma by the third varying, I get an interpolated value at that position P that I want, which is right about here, right, in this case. But we are going to do that pixel by pixel with all the different points P's that we have inside the triangle. Got it? So the question is, how do I find alpha, beta, and gamma, given that I have vertices V0, V1, V2, and a point P inside my triangle? The way that I'm going to approach the explanation is by looking at this geometrically, right? So you will see that alpha can be seen as the area of the subtriangle that you have right here. So alpha has to do with how much we pull to that V0, right? So it's kind of like how much I pull. This percentage right here of how much I pull to that vertex can be seen as the area of this subtriangle right here. And when I talk about area of triangles, I want also to explain something. Do you remember when we spoke about cross product? The cross product has everything to do with the angle of those two vectors, and as the angle rotated, we had that magnitude of the cross product going positive, growing, and then shrinking, going negative. So the magnitude, the length of the cross product had everything to do with the angle of vectors A and B. But you can also think of the magnitude of the cross product vector as the area of the parallelogram that is formed between A and B. Do you see how vectors A and B, they form this parallelogram, almost like this plane parallelogram? The magnitude of that cross product, the length of that cross product, is the area of that parallelogram that is formed between vectors A and B. And this is super important because if we go back here at this definition, we can find the area of this parallelogram, right? Well, this is a triangle, but I can think of it as a parallelogram. The area of the parallelogram by using cross product. So this vector right here, cross product, that vector is going to give me this area. I can think of it as alpha is the cross product between V1, V2, so V1, V2, and V1P, V1P, V1, V2, V1P is going to give me this cross product, the area of the parallelogram, and the alpha weight is the subtriangle, this area of the subtriangle divided by the area of the entire triangle. This is going to give me the percentage, right? This is the percentage that we are pulling to V0. So the area of that parallelogram, that is this alpha red here, divided by the area of the entire triangle, which is V0, V2, and V0, V1, right? So V0, V2, V0, V1 is going to give me the area of this entire parallelogram right here. The entire area divided, right? This red divided by entire area, This is my alpha. Going even further, do you agree that this thing right here, V1, V2, cross product V1P, is the same thing as our cross product from before, that W0 that we calculated? So this thing right here I can just replace, and my alpha is going to be the W0 that we had before, that we already calculated for each one of the points, right? Is going to be that cross product between the edge and the point, divided by the area of the entire triangle. Easy stuff. And it is no surprise that it's going to be repeated for beta. So what is this area beta right here, which is how much we're pulling to V1, right? What is this percentage in relation to the entire triangle? Well, it's going to be V2, V0, so V2, V0 cross product V2P, so the edge and the point. This is the same as our W1 divided by the area of the entire triangle to get the percentage. So V0, V2, V0, V1, that gives me the parallelogram of the entire triangle. This division is the ratio that is going to give me the percentage that is this area beta right here. And we can reuse that W1 that we had before. Easy stuff. Of course, same thing with my gamma, right? My gamma is going to be that thing to find the blue one divided by the area of the entire parallelogram. I can just use, this is the W2, right? Because it's the edge and the point P that is going to give my gamma, which is the weight that I am pulling to V2, this percentage, which is also can be seen as this area of this triangle right here. I'm talking about area of the parallelogram, but if we divide everything by 2, is the same as the area of the triangle divided by the area of the triangle, so this thing right here. Right, so if we look at the code, it's going to be super simple, right? We have the triangle field before, we have those 2 for loops, we have my point P, I had my float V0, V1, and V2, right? I'm just thinking about floats right here, but you know that we're using fixed point numbers. Do you remember how we work already calculating W0, W1, and W2? All I have to do is, first, I need to find the area of the entire triangle, of that parallelogram, which is basically the cross, right, the 2D cross between V0, V1 and V0, V1, V0, V2. So I get the area of the entire parallelogram, the entire triangle. And what do I do here to find alpha, beta, and gamma? Alpha is going to be W0 divided by the area. Beta is W1, that cross divided by the area. And gamma is W2 divided by the area. Super easy, right? So only work with these ideas of W's that we already had before, the cross product between the edge and the vector. Now we can divide by the area. These are going to be our percentage, right? The percentage values, alpha, beta, and gamma. How much are we pulling to V0? How much are we pulling to V1? And how much are we pulling to V2, right? So all these 3 vertices, what is the weight factor that we are pulling? Alpha, beta, and gamma. Again, why is it important for us? Because we can interpolate values by using the alpha times the V0, the beta times the V1, and the gamma times the V2. Interpolation of values, as easy as it gets. Using barycentric coordinates, right? This scary name thing, which is, as you saw, super easy. Right? So we approach this by looking at the area of the triangles, the area of the sub-triangles as those percentages of weights, and of course, thinking about the area of the entire triangle, percentages, alpha, beta, and gamma. Great stuff. Charming. Which means that we could come here to our code, and I'm going to start adding a couple of options here. So remember how we had 5 vertices? I'm going to remove the last one. Let's just have 2 triangles. If I go down, I do not have this anymore. And I don't have this one. So we're just going to have 2 triangles because I think it's simple for us to see what's going on. So if I come here to line 19, I am going to add a new type, which I'm calling color underscore T, which has exactly what you expect, right? RGB, and I'm saving them as this 8-bit colors, 8-bit numbers, because I am going to add a new array of colors for the vertex 0, vertex 1, and vertex 2. So I'm going to have for vertex 0, full red, right, 255 red, no green, no blue. For the second vertex, I'm going to have no red, full green, 255, no blue, and you got the idea. For the last vertex, I'm going to have no red, no green, and 255 blue. I'm just choosing to write them in hexadecimal notation, but it is 255. So the idea here is that now that I have these values per vertex, I'm going to have to go and interpolate these 255 to something a little bit smaller for the vertex 2, vertex 3, vertex 3. So I'm going to have this interpolation, this blend of a little bit of red, a little bit of blue, a little bit of green whenever I am inside that triangle. And for that, we're going to interpolate using those barycentric coordinate values that we just saw on the slides, of course. And if we go to our fill function, right about here, after I found my bounding box, I am going to choose to compute right here. I'm going to have our float area, which is the computation of the area of the entire triangle, actually the parallelogram, right? Because we are using the cross product between V0, V1, and V2. So this is the area of that entire parallelogram of the entire triangle, which we can use, of course, cross product to find that. Now that we have the area of the triangle, which is being computed just once per triangle here outside our for loops, right here, after I test if we are inside the triangle or not, I am going to have that alpha, beta, and gamma barycentric coordinate values, right? Those weights that we have to go and multiply by our vertices to interpolate. So here we have alpha, beta, and gamma, and we just saw that it is the division between the W0 by the area, W1 by the area, and W2 by the area. Because now that I have alpha, beta, and gamma, these percentages of weight, right, between 0 and 1, these normalized percentages, I am going to go and interpolate red, green, and blue values using these barycentric weights. So do you see how I have something called A, R, G, and B, new variables? A is always going to be FF for now, so I'm not going to change the transparency. But I have the red component, which is the multiplication between the alpha weight times the colors of 0.r plus the beta weight times the colors of 1.r plus the gamma weight that multiplies colors of 2.r. So this is the interpolation of all those three vertices red component, and I do the same thing with green, and I do the same thing with the blue components of all those three vertices, using the alpha, the beta, and the gamma, multiplying, interpolating the values of the vertices to get a color that is in between those values, right? Wherever I am inside the triangle in this point P that I am currently visiting. Right, so now I have these three variables R, G, and B, which are 8-bit numbers. All I have to do is really create and combine them into this 32-bit color, right? So I can actually go and pass to the draw pixel function. So let me just create something called interpolated color, and I can initialize with, I don't know, nothing, right? So I just initialize with some value, and then I have to use this interpolated color. We're gonna combine those R, G, and B values into this one 32-bit color, and then we're gonna pass the interpolated color to our draw pixel. So let's look how we can actually combine those three 8-bit colors into one big 32-bit color. I'm going to save your time, and I'm going to paste what I have here already. So I am always getting that interpolated color, and I am doing a bitwise OR with the component that I want, blue, green, red. So I do a bitwise OR to kind of combine those colors, but I'm always shifting, right? Bit shifting 8 bits every time. So I can actually go to the next color, go to the next color, go to the next color. So I'm basically populating this 32-bit interpolated color, kind of using bitwise OR and bit shifting, right? 8 bits at a time to go and push those components to the left every time. And at the end, after I find alpha, blue, green, and red, I have at the end my interpolated color, which I go and I draw my pixel at that position, X and Y. That also means that I really don't need to have this color being passed as a parameter anymore, right? So we don't have this solid full color here. So we don't need this. And I think we need to change here at the end. We don't pass this parameter. Easy stuff. Let's see if that works. If I make, great. And if I make run. Now, would you look at that beautiful interpolated pixels of our triangles, right? This is absolutely great news. We have vertex 0, which was full red, vertex 1, which was full green, and vertex 2, which was full blue. And then every pixel that we are visiting gets an interpolated value that is this kind of blend, right? Using these barycentric coordinates. How much am I pulling to this red vertex? How much am I pulling to green? How much am I pulling to blue? Depending where I am visiting, these things get interpolated. And this is true for this triangle, and this is also true for vertex 0, vertex 1, and vertex 2 of this triangle right here. We are still using few conventions. We are still using that Pineda rasterization algorithm that goes pixel per pixel. This is absolutely great news. And as always, I want to point out that this is true for the colors, right? So since we have color for vertex 1, color for vertex 2, and color for this vertex here, now we are using colors and interpolated color values, but nothing stops us from using this as texture coordinates, right? So you can have a texture UV mapping here, a texture UV mapping here, and a texture UV mapping here, and then you just go and you do this affine interpolation of values, getting a different pixel from that texture each one of these pixels, and that is great news. And we actually do that in our course, where we go and we do this texture mapping into the triangles, because the reality is that if you have a 3D modeling software, Blender, Maya, 3D Max, they go and they map this PNG images into the faces of the triangles, or these JPEG images. They have these texture files that they map, and they have these coordinates, and then all we have to do is go and interpolate to fill the triangle face with these interpolated values of the texture that was mapped into these vertices, right? This is texture mapping 101. Of course, there's a lot of other details, right? Whenever we start rotating and applying perspective to these triangles, we have to be careful. So there are some other mathematical techniques that we have to use whenever we have perspective and depth, but I'm not going to go that far here. I think I'm happy with the way that we are interpolating the colors for now. Speaking of making our rasterizer a little bit better, right? The first thing that students usually ask me is, okay, Gustavo, it seems a little bit wasteful that we are visiting all the pixels of the bounding box, right? Regardless if they are inside or outside. It seems that we are wasting a lot of processing power going all these pixels from the bounding box, because right here we have all these empty pixels that are inside the bounding box that we are visiting but not rendering. Right here as well, we have all these empty pixels. So isn't there a way that we can avoid this waste whenever we are visiting all the pixels? And that is a valid question. If you come here back to the Juan Pineda article, you will see that they talk about edge functions, all those good things. And they also mention these ideas of traversing the polygon, right? So we start with this naive idea of traversing all the bounding box from left to right, top to bottom. So we go and we scan all these pixels. And this is not really optimal, right? They talk about trying to be smarter. So for example, if you start and you enter the triangle, all the values will be positive, and as soon as you change from positive to negative, do you agree that we left the triangle and we should be able to go and start going to the next one down? We don't have to go and fill all these other ones. Does that make sense? So at the moment that we are traversing and visiting pixel per pixel, if all these values were positive, and we found now a negative one, meaning that we left the triangle, we are outside, we don't have to go and visit all these other pixels. We left the triangle, we should be able to go to the next one down, right? And then they speak about some other techniques, some issues with this approach. They talk about maybe a different approach of going to the middle and then visiting to the left or to the right. So there are different techniques that you can approach. I am not going to do that, but I am going to explain to you something super interesting, which is, do you remember how we have our W0, W1, and W2 right here? I want to show to you a pattern that happens. So let's just do this. Right here, let's just create these ugly global variables, something called old W0, old W1, and old W2. And I am going to, in the moment that I compute W0, W1, and W2, I'm going to save these values. So old W0 equals the current W0, and you get the idea. So I save the W0 into the old W0, W1, and W2. Let me just show what happens. W0 minus old W0. Let me just show these values right here. W0 minus old W0. So let's just look at the difference between the current W0 and the previous one always, right? So I want to look at this delta, this difference between W0s that we have. And this is going to be true for W1 and W2 as well. But let's just look at W0 for now. Right, let me just pause and go back here. Look at that. Do you see? The difference between the current W0 and the previous one is always constant. Well, it looks like it's constant, right? So 40, 40, 40, 40, 40. If we go up, 40, 40, 40, 40, 40, 40, oops, minus 1960, but then it continues again constant. You see constant, 40, 40, 40, 40, 40, until that value again, minus 1960. Constant again until 1960. So we have this idea of having everything constant and then you have this big change, and then constant, one big change. Right, what is going on here? So what if I tell you that the way that we are navigating our bounding box of pixels, right, we're always going from top left, right, 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 and then down, right, 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 right. Everything is a straight line, right? We're going from top, straight line, and then we go down, straight line as well. So the nature of this straight line navigation that we have, it is the reason why we see this constant increment between the W's, right? The W0 to the old one, and the W1 to the old one, and W2 to the old one. All these different W's per edge. The reason why we see that is because barycentric coordinates, right? The values of those barycentric coordinates and the values of the edge function, they are constant along the lines that are parallel to an edge. So we have the values of the barycentric coordinates for one edge, they are always going to be constant along all those parallel lines for that edge, and also for the other two edges as well, right? So the values are always going to be constant in these parallel lines along the edge. And the fact that we are navigating straight lines, right? Since our edges are straight lines and the navigation that we are performing is straight lines as well, we have this constant increment between the W's that we are visiting one by one. And you should be getting pretty happy by now, because that means that we do not need to compute that edge function, that edge cross, per pixel. Because if we find this difference of W, right, delta W in the x-axis, all we have to do is just go and increment by that delta, right? So as I go one pixel to the right, I increment by the delta W for that column. And then next pixel to the right, I increment by delta W. Next pixel to the right, increment by delta W. This will only change when I go and I move from one scan line to the next one down. In that case, I have to just go and update and increment by delta W down. Do you see? So this delta X and delta W, this difference is always going to be this constant increment. And this is actually what we're going to do to try to avoid a little bit of the CPU cycles, right? So we don't have to waste CPU cycles computing that edge function and W0, W1, and W2 all the time. Only the simple increments, just an addition, will do the job per pixel. And you could approach this problem by thinking, well, if I compute the edge function, right, of that top leftmost point that I have in my raster, and then if I compute the edge function of the pixel to the right of that one and the pixel below that one, I will find this delta W in the column, right, in X, and the delta W in this scan line per scan line. So I'm going to have this delta W X and delta W Y. But we don't have to really compute these three edge functions there, because I'm going to show to you that we can derive these ideas of what is this delta W in the row and delta W in the column, right? Column per column that we have. And to start this conversation, remember how we have, let's just isolate and look at one edge, right? So that cross product between V0 and V1 and V0 to P, you remember that that was given by that edge function between V0, V1, and P, right? So we find the edge V0 to V1, and we find that vector that goes from V0 to P, take the cross product, has to be positive to be inside the triangle, right? This, we should be tired of hearing this by now. So I want to start thinking about this. This right here, we saw that it is basically the cross product, right? That 2D cross product between the edge and that point. If you think about the cross product, it is the edge cross product, that vector to the point. So do you agree that this vector right here is the edge? V1x minus V0x, V1y minus V0y, this is the x and the y of that pink edge, right, from V0 to V1. V1 minus V0 will give me that vector from V0 to V1. So this is the edge cross product This is that vector that goes from v0 to p. So px minus v0x, py minus v0x, that is that yellow vector. So this is the cross product, right? This is exactly what we had before, is the cross product between these values and these values. We also saw that if we break into this fake 2D cross product, it is this one times this minus this one times this. It's almost like the determinant, right, of this kind of expanded matrix that we have. So this times this minus this times that will give us this multiplication right here. So v1x minus v0x times py minus v0y minus px minus v0x times cross, right, v1x, right? So we basically cross multiply minus cross multiply, cross product, right? The magnitude of the z component of that vector that is perpendicular, that imaginary vector that is perpendicular to the screen. This is the cross product that we were using, the 2D cross product hack that we had. So I'm going to start doing a couple of things. So let's expand this thing. Do you see how we have that multiplication? Let me just distribute that multiplication, right? So v1x times py, v1x times v0y. So I'm just going to distribute that multiplication and expand both of these things, this multiplication and this multiplication as well. I'm going to go and distribute this multiplication to open everything. So I'm going to get v1x times py, and then I distribute v1x times v0y, right, minus v0x times py minus plus v0x times v0y. And then minus, I'm just keeping this minus and then doing this, distributing this multiplication. px times v1y minus px v0y, v0x times v1y plus v0x v0y. Right, so now that I have this thing right here, again, let me just do some simple algebra and flip everything, right? Since this is negative, let me just flip all the signs of this one right here. So that is exactly like that. I just kept the first one exactly as it is, and then I just flipped. Minus, 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 plus, minus, minus, plus, minus, minus, plus. So I just flipped all the signs. Right, so now that we have this thing right here, I want you to pay attention to the fact that, do you agree that we have both px multiplying both v1y and multiplying v0y? So since px is multiplying both of these terms, I can factor px out and just have everything in this multiplication of px, but also py, right? So py is multiplying this value, but is also multiplying v1x there at the first term. So I can group everything. I can factor that px and py out and have this everything in terms of this px and py multiplication. And also, do you agree that v0x, v0y minus v0x, v0y, this I can basically cancel out? So now that I don't have those two terms anymore, let's just group everything in terms of px multiplication and py multiplication and see what we're left with. Right, so now I have px multiplying both v0y minus v1y, and then py multiplying v1x, which is the first term there on the far left, minus v0x. And then I have all these things that are just left, right? So everything else that is not multiplying py and px. This thing right here, do you see this term that is multiplying px and this term that is multiplying py? This is actually our difference, the delta between the previous column and the second column, and the delta between the previous row and the second row. So these things right here, they are going to be our delta w in the column domain. So this is the delta w in x, and this is the delta w for the rows in y. This thing right here is for that edge, right? So from v0 to v1. From v0 to v1, the delta that we're going to use, the difference of w's that we're going to just increment every time, this is going to be x by x, column by column, and this is the delta y row by row. But if we want to find the delta w and delta w in x and y for the different edge, let's say from v1 to v2, it's going to be the same thing. I just have to go and change this edges, vertices that I have, right? Instead of v0, v1, it's going to be v1, v2, and then if I want to find delta w column and delta w row for the edge that goes from V2 back to V0 is going to be exactly the same pattern, but changing the vertices. So the delta W in the column domain and the delta W in the row domain, scanline per scanline, is going to be always the first vertex Y minus the second vertex Y, and the difference of W in the row domain is going to be the second vertex X minus the first vertex X. This is how we get those deltas, those difference of W's that we have to go and increment every time that we are visiting the pixels, both column by column and also scanline per scanline. We have to just go and nudge increment by this delta row every scanline that we jump. All right, so this is exactly what we're going to do in our source code. If we come back here, let me just remove everything that we had before, printing this W0 and etc. We don't need this old W0 anymore. We got the idea of the pattern, right? So what I'm going to do is, as soon as we enter our fill routine, I'm going to compute those deltas per edge, which, as we saw in the slides, is we have a delta W0 column, W1 column, and W2 column, which comes from the first vertex Y minus the second vertex Y, and that is true for all the other ones. And the delta in the row domain, right, Y by Y, scanline by scanline, comes from the second vertex X minus the first vertex X, and that is also true for all the other edges, W1 and W2. So now that I have this delta W0 column, delta W1 column, W2 column, and delta W0 row, row, and row, I can start using, instead of using as we did before, remember, computing P and using this computation to find W0, W1, and W2, I am not going to have this per pixel anymore. And what we're going to have is, outside our loop, I am going to compute what is that first top leftmost pixel of our bounding box. So I'm going to have something called P0, which is that point at X min, Y min, right? So this is the first point of our bounding box, and I'm going to compute the W0 for the current row, the W1 for the current row, and the W2 for this current row that I am, which is the computation of that edge product between the vertex V1 and V2 and P0, V2 and V0, and V0 and V1. So I have one point, that top leftmost point, at position X min and Y min, and then I compute this W0, W1, and W2 for that first top leftmost point. And even more importantly, I can come here and apply that bias right here, because we already have this bias computed per edge, so it doesn't matter what I do. Plus bias 0, plus bias 1, and plus bias 2. So this is the computation of the edge and the bias of the first point, right, the top leftmost point of our bounding box. Because per scanline, right, as we are navigating scanline per scanline and column per column, per scanline, I'm going to initialize, I'm going to have a float W0, right, at this current scanline, W0 starts always with the W0 row, W1 starts with W1 row, and W2 starts with W2 row. So I always initialize W0, W1, and W2 per scanline with this leftmost value of this row. I don't have to do anything here inside. All I have to do is, at the moment that I change column by column, W0, W1, and W2, they have to be incremented by that delta in X, or what I'm calling the delta column per column. And in the moment that I change my scan line to the next scan line, I have to change that W0 row to be bumped, to be incremented by that delta in the Y domain, or what I'm calling the delta row. So as we start our triangle rasterization fill routine, we go and we compute that top leftmost point of the bounding box, and we store in this W0 row, W1 row, and W2 row. So W0 row, row, and row, they are going to have always the value of the start, the leftmost value of that row. Because as we are in this for loop column per column, I'm always bumping, incrementing the W0 by the delta column per column, and in the moment that we go and we change to the next scan line, I have to go and increment the delta row, the delta Y, which is what we do, the W0 row incremented by that one, because the next W0 row will be incremented by the delta Y. So this is exactly what we're doing with this algorithm. This thing right here was an inspiration from the Fabian Gissen's blog, and the whole reason why we're doing that is because we want to avoid computation. Now we have only basically this 3 additions per pixel, right? And the least we do per pixel, the better is going to be our performance, hopefully, right? And look, the output of this is probably not going to be something extremely interesting, but there you go. So this is exactly what we had before, but now we are performing a lot less per pixel, so better performance. I'm not measuring anything, I'm not doing any profiling, but you get the idea. And this is one of the reasons why this algorithm right here is so popular, right? You don't have to compute all of these things per pixel. Only computing the first one and finding those delta in the column domain and in the row domain is enough for us to just go and start bumping, incrementing each one of those values per column and per scan line. Great stuff. And we could call it a day, but I want to discuss a couple of extra things because, let's be honest, right? In the context of game development, the triangles are not going to be static all the time. We want to move things around. So let's think about moving, translating, maybe rotating these triangles around and seeing what happens. So if you come here, let me just, if I open vec2.c, and if we go down, let me just add a new function that knows how to rotate a vector. So this function right here is called vector2rotate. It knows how to go and rotate a vector around a certain center of rotation. So the pivot point of that rotation, I have to pass what is the center of the rotation by a certain angle, which is of course in radians. So I'm not going to waste too much time explaining this function. All you have to understand is that the first thing that we do is we have to translate to the center, right? So I just go and I subtract the center, I go to the origin of my system, and then I actually go and I perform the actual vector rotation. Remember those formulas? X times cosine minus y times the sine. This is the actual rotation of the vectors. If you don't know why this mathematics works, I have a video that you should definitely check out, right? How to perform vector rotation. Don't forget that one. This is what goes and actually goes and rotates those vectors around by a certain angle, and I have to just go back and translate things to where they were. So I go to the origin, I rotate, and then I go back to where I was. This is vector rotation. The only gotcha here is the fact that since our rasterizer, so far, we are only talking about pixel integer values, I am always rounding that rotation value. Since it is a float, right, that rotation gives a floating point number. I have to just round x and y to return always the integer part of our rotation. That's what I'm doing right here, just rounding things out. And then I return this rotated vector. Let me just quickly copy this prototype, go to vec2.h and expose this one. Perfect. So now we can call the rotate. Because if we go back to main.c, in our render function, right here, we should be able to start rotating this v0, v1, v2, and v3 around before we ask to fill those triangles. So I'm going to start, we're going to have this concept of an angle that's always incrementing, and this is what I'm going to use for that angle. I am using a function called SDL getTicks that returns the milliseconds since we started SDL, and then I'm dividing by 1000 to just get this in seconds, and then I multiply by this 0.1, this factor of how fast I want that rotation to happen. So this is going to be 0.1 radians per second, which is actually not that fast, right? But since now we have this angle, I should probably think about creating that idea of that center point, right? That pivot point around the rotation, which we can have this vector to center, which comes from the screen width divided by 2 and the screen height divided by 2. So I'm rotating everything around the middle of the screen, right? At the center of our screen at 64, 64, x and y. because I'm not going to have this anymore, v0, v1, v2, and v3, they're going to come from the rotation of those vertices. And we can do that by simply calling v0 is now the vector to rotate of that raw vertices at 0 around this center point by this angle, and I do exactly the same thing with v1, v2, and v3. Now that these vertices are rotated, I can just ask to go and draw and fill those triangles at those rotated vertices. That should be enough. Let's see. Make, beautiful, and if we make run, would you look at that? So this is great news. We are rotating our vertices around this center of the screen. Everything looks okay. We are rotating the vertices and everything gets rendered exactly, right? We are computing the bounding box, we're computing the rotated edges. Everything looks amazing. Well, not amazing because, as you can see right here, things are a little bit jittery, right? Everything jitters. It's almost like we are always snapping to the grid. And this is exactly what I would expect from a rasterizer like ours that is always integer-based, right? Everything is pixel. Our pixels are always just integer one by one. So everything snaps to the grid. The vertices of those triangles are always snapping to the grid. And that is also why we have that rounding, right? As we rotate, we always snap to the nearest integer. This thing right here, this jitter, right? This polygons jumping around, this is actually pretty classic in all those old school rasterizers that did not use subpixel accuracy. Right? So if you do not have subpixel movement, and if you don't consider these values inside the pixel, right? If you have this floating point, this fractional part of numbers, everything is going to jitter a little bit. And if you think about classic game consoles, right? So for example, PS1 games, right? This PlayStation 1 games. PlayStation 1 games, they were known for having these polygons jittering around. And this jitter came from the fact that PS1 games and PS1 did not have this subpixel rasterizer. So everything was a little bit jittery, right? Besides all the other artifacts that PS1 games have, polygon jitter was one of them. And again, this should be okay, but I do want to talk to you quickly about these ideas of subpixel precision, right? Because we need to consider what does it mean for us to have this subpixel movement, right? Vertices that move inside the pixel. So nothing should be snapping to the grid. We should be able to have these floating point values or something like floating point values that consider this decimal part, right? This fractional part of the vertices. And to start this conversation about subpixel movement, I want to look at our raster, right? So I'm zooming in here so we can actually see what happens pixel by pixel. In our current implementation, we are using only integer values, right? So it doesn't matter what we do with the vertices of our triangle, we are always snapping to the closest integer values. We are rounding things to the closest integer value. And the W0, W1, W2 edge functions are also integer values. The fact that we have the area of the triangle, everything is integers, right, so far. That is why we have everything is snapping to the grid, jittering around. We want to achieve something a lot smoother, right? So instead of having this rasterization from one integer pixel value to that other pixel value, I want to have something smoother that adapts as we are moving those floating point numbers around. So let's just say that instead of using integer values, we change everything to use floating point numbers, right? That means that whenever we rotate our triangle vertices, we are not rounding things off anymore. They are actually assuming those decimal values, right? 6.7789, 4.0002. So all these floating point numbers, this is what happens. Now, the vertices of the triangle, as they rotate, they can assume values that are internally inside the pixel, right? So let's just think that that round right there is rotating. It navigates inside the pixel. I want to have my rasterizer respecting that subpixel movement and changing the way that we rasterize this line right here based on that subpixel movement. I don't want to go integer to integer. I want to respect, right? It has to be the subpixel movement, smoother. Let's just imagine what happens in this scenario, right? So let's just say that we have this vertex of the triangle and we have that vertex right there. As that vertex is moving inside the pixel, let's just say that it's moving down inside the pixel. Look at what happens in a subpixel rasterizer as that vertex is moving down. Down, down. Do you see how the rasterizer changed And the way that this line is now painting the pixels, it changed what pixel gets displayed here. And as we continue moving down, 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 it changed, now it paints this one. So as we are moving down, pixel by pixel, subpixel movement, everything changes, right? The way that we are rendering this line. So it's almost like we are, depending on the position of that vertex, subpixel position, right, internally inside the pixel, we are adapting our rasterizer to have this smoother rasterization effect. Let's look at how this really is implemented. And the first thing that I'm going to do is I'm going to go to vector.c, and I do not want to round these rotation values anymore. So I want to get the actual floating point rotation with decimal part out of our rotation function, because our main.c has to start changing a couple of things, right? So let's see what needs to be changed. Nothing, nothing. Right, so the first thing is our edge cross, since now these vectors a, b, and point p, everything can have this floating point x and y values. This thing can return a float, so that changes, right? This cross product can return a floating point number. Let's see what else. So now our triangle field, the vertices v0, v1, and v2, they can have x and y with floating point values. Let's just think about the bounding box. So x min, y min, x max, and y max. The way that I am navigating pixel by pixel, I still think that we should navigate discretely, pixel by pixel, integer by integer. So x min, y min, x max, y max, I think they should be integers. The only problem is, whenever we are taking the minimum of these floating point values, I'm going to have to round them. Actually, I'm going to get the floor of the minimum, and I'm going to use the ceiling, the ceil function, for the maximum. Does that make sense? So I'm just pushing it down for the minimum and pushing it up for the maximum. Right, so now we have this x min, y min, x max, and y max correctly computed. Let's think about this. Well, the deltas, of course, they have to be floating point numbers. Both for column and for row. Right, look at that. The area I already calculated as float, so nothing to change here. Our bias, is a problem, right? Because before we were computing everything pushing -1. So this is what I'm going to do. I'm going to change this bias to float, but we're going to have to think about this very soon. We're going to have to think about this smallest offset that we have to push to respect our rasterization rule. Okay, what else? Right, so this thing right here also float, float. And right, while I am at it, let me just discuss quickly this. Do you see this point 0, which is that first top leftmost point that we are computing and checking with the edges, right? Checking the edge cross with that point 0. One thing that you will see most blogs and programmers suggest is, whenever we are comparing if a pixel belongs to that edge or not, right? Whenever we are taking the cross product, the edge function between a pixel and that edge, instead of using the top left of the pixel, we should use the center of that pixel, right? So I'm going to offset, add a little bias of 0.5 in x and 0.5 in y. Because then we are always testing with that edge the middle, right? The exact middle point of that pixel. Right? So this is one change that you will see most programmers out there do. And then we actually compute the W0 row, W1 row based on this P0 at the middle of P0 plus the bias, so that doesn't change. Now that we are pixel by pixel, what do I need to change? I already declared W0, W1, and W2 as float, so nothing to change here. Let's see what else. Alpha, beta, and gamma, they are floating point numbers, right? They are their value between 0 and 1. This is just colors, integers, that's fine, colors. I think that's it, right? Our angle is still in floats, so that looks okay. Let's just see how that looks. now that we are performing all these computations and using floats all the way down in our rasterizer. Right, and if we run, I expect to see something a lot smoother than what we had before. Right, so good news and bad news, right? First of all, I know that you can see these gaps. I can see them as well, of course. We're going to have to talk about this very soon. This has everything to do with that bias, that fill convention. We're basically squeezing and pushing everything a lot more than we should, right? -1 is probably a lot more than we should. But ignore this thing for now. Let's just look at the way that our rotation is happening. This is a lot smoother than before, right? And I want you to pay attention at what happens to the edge. Look at this edge. Do you see how smooth it is, this rotation? Look at this middle right here, smooth. This edge right here, look at how the rasterizer adapts to these floating point values, and the line is a lot smoother. This is absolutely great news. We have this subpixel accuracy and the subpixel rasterizer, right, respecting these floating point values. But speaking of floating point values, what about our gaps? Well, it is no surprise that we have an issue right about here. Because the question is, okay, since we are not using integer values anymore, what is this smallest offset that we have to push and squeeze everything in the edges so they do not belong to that edge? Before, everything was integer, it was super easy, right? But now we have these floating point values. What is the smallest floating point value that you have to push those values, the pixels of the edge? Is it 0.001? Is it 0.0000001? What is this small offset, right? What is small enough and what is not, and big enough so things are also being respected, right? Our triangle rasterization rule. Well, that is not really an easy question to answer because of the nature of how floating point numbers work. If you think about floating point numbers, they are almost like this scientific notation of numbers, right? We use this exponent, a sine, a mantissa, so we have this fancy way of representing a huge amount of numbers by using this smart way of raising something to an exponent and then changing the sign. So we do have this pattern, this standard that uses this fancy way. But the reason why we cannot answer this question, what is the smallest possible offset that I can push that number, is because floating point numbers, they are discrete, but they are not equidistant between each other, right? I don't know what is this distance. This distance between one floating point number to the next is not constant. They are not equidistant, so I cannot answer this question easily. So what should we do? Well, if you go and you look at suggestion, right? If we look at Christopher's Dichron's blog, he talks about these ideas of having these different resolutions depending on the floating point value itself, right? So we have these different resolutions depending on where we are in this kind of fake number line that the floating point numbers try to represent. So we have these issues with floating point numbers, calculation issues, accuracy, precision, and the solution that you'll see most programmers give you is to use fixed point math. Why is it important for us to use fixed point math? Because fixed point numbers, they use a constant number of bits to represent the integer part of a number and a constant number of bits to represent the decimal, fractional part of that number. So for example, you could use two 8-bit numbers, 8 bits for the integer part and 8 bits for the fractional part to represent these fractional values. Right? So you have 16 bits, you break them into 8 and 8. But knowing that we have only 8 bits for the fractional part gives us this consistency, right? We know what is the resolution that we can represent, what is the smallest value that we can represent only using those 8 bits. And it doesn't have to be 8 bits. You can use, for example, 32 bits and break these 32 bits into 16 bits for the integer, 16 bits for the fractional part. But you will have this constant resolution, right? What Christopher calls the resolution of these fixed point numbers. And if you look at implementation details, he actually talks about fixed point numbers and the relationship with pixels and subpixels, right? Because if you have something even as simple as 8 by 8, right? You have this 64 resolution subpixel. You know that the smallest offset that you can move is always this small 1/64th, right? These fractional values, they are equidistant with fixed point math. And in this case, using fixed point precision, instead of moving integer by integer, pixel by pixel, you move this subpixel by subpixel at these discrete intervals, but inside the pixel, right? It's almost like you break the pixel into these small subpixels, fixed point representation. So the question now is, okay, are we going to go and replace everything that is float to use fixed point math here in our code? We could do that, but I am not going to do that, right? I think it is outside the scope of this video. What I'm going to do is I am going to live with the shame, and I'm going to just find something that is small enough and big enough so we have something visible on the screen. So let's just say, I don't know, minus 0.0001, right? We're gonna be reckless and we're gonna just live with the shame. Maybe this is a value that is small enough, big enough. Again, is not going to be perfect. I want you to understand that this thing that we're doing is definitely not perfect. We are going to have a little bit of overdraw and overlap here and there because this thing right here is definitely not perfect, right? We cannot answer this by using floating point numbers. But I think we're not going to have gaps or too much overdraw using a small offset for this bias for now, right? But remember, if you really want to fix this, the answer is to fix it. And you know what? This is what I'm going to do. I'm going to leave in the description of this video, I'm going to leave a link of a very simple implementation of fixed point math for this code using a fixed point library in C. And you will see that it's super simple. It's basically just us replacing everything that is float by this new type that the library provides called fix16_t. So this library provides 16.16 fixed point format. So it uses 16 bits for the integer part and 16 bits for the fractional part. Just by using this small library and replacing everything that is float by fixed point, you will see that we are able to go and improve the accuracy of our fill rule that we are using, right? Our bias here, this offset, because that offset is constant, right? I know that I only have this 16 bits for the fractional part. I know what is the smallest value that I can represent and offset those edge pixels to go and not display them or display them depending on what the fill rule is telling us. Good stuff? Right. So let's just see how this looks. We make, and if we make run, right, fingers crossed. Right, so look, I don't see any gaps. I'm pretty sure that we do have a little bit of overlap and overdraw here and there, but I'm just going to leave with that. Right? If you want the actual fixed point implementation, just go in the description. You will see my GitHub page there. You'll see nothing super hard. But if you look here, everything is a lot smoother than before. We do have subpixel precision rasterization. And of course, the fill rule is there. It's just not perfect as we are right now. But you know what? I think this is pretty much where I'm going to stop. I'm going to call it a day, and I'm going to appreciate what we were able to achieve here. And everyone, it goes without saying that this thing that we just created right here, right, painting pixels on the screen is just the tip of the iceberg of what 3D computer graphics is. All these things that we did, the fact that we are painting, rasterizing, right, looking at this raster, painting pixels on the screen, this is just the rasterization part, and it's just a small subset of rasterization part, and we are kind of cutting some corners here and there. But I just want to point out, I'm actually happy because we covered a lot of ground, right? This video is actually super important. We cover very important details of, right, the mathematical details of cross-product, checking if it is inside or outside, the fact that we are using an algorithm. Remember how we are visiting pixel by pixel. This thing can be parallelized, right? If you go and you have proper hardware, or if you actually go and you use maybe a SIMD or multi-threading, you can parallelize this thing, because then one core is responsible for one computation, right? And as you go and you compute that edge product, or if you compute that edge function, each core is going to go divide and conquer and compute all these things in parallel. And this is actually how most GPUs will approach this problem, right? Remember, GPUs, they have these things implemented via hardware, right? So everything is super fast. You have all these mini small cores that know how to compute one little small thing. They go, everyone computes something and then returns back at one instruction, right? Everything is super, super fast. Look, it also goes without saying that if you are talking about a software rasterizer, there are a lot of details that we have to implement, optimizations, right? We have to really squeeze everything if you are talking about a software rasterizer on the CPU. And also goes without saying the fact that this thing that we did right here, it is no surprise that most of the time these things were implemented using a special assembly routine, right? If you are talking about PS1, GBA, right, the Game Boy Advance games, if you're talking about MS-DOS games, painting pixels, usually you have this special assembly routine that used to do that, right? You have several resources. For example, a very classic resource which kind of dealt with things using rasterization and using x86 assembly was the classic Micah Brash book, the black book, right? The graphics black book. There was a lot of x86 instructions and routines for us to go and rasterize and render things on the display. But that was a long time ago whenever we actually wrote software rasterizers for computers and machines that could not parallelize things. What we are doing right here is basically using the processor to kind of naively implement what the GPU might do, right? Using barycentric coordinates, using these edge functions, cross product, all this parallel algorithm that Juan Pineda proposed back in his article. In the real world, right, in this modern 2023-24, we will have this 4K resolutions, everything is super high resolution, so everything is happening pixel per pixel, fragment per fragment in your display. And you have this beautiful, beautiful result, super fast, of amazing output, but everything at the end of the day needs to be rasterized in your pixel raster on the screen, right? There is no escape. You might have this powerful GPU, you have this dedicated graphics card, but rasterization, right, the fundamental of rasterization is always there. Everyone, I am aware that YouTube is not really designed to be an education platform, right? Probably right now YouTube is throwing you lots of crazy thumbnails to distract you and to go somewhere else, right? To take the attention of learning. This is not really an education platform, so if you really want a comprehensive course where we look at all the stages of the graphics pipeline, we learn how to render lines, triangles, rotate objects, all the stages, right? World transformation, projection, backface culling, clipping. There's a lot more to 3D graphics than just what we saw right here. If you want that, you know where to find me. I teach at picuma.com. We have several courses on old game console programming, assembly programming, computer graphics, physics simulation. So there's a lot of really cool, tasty stuff there that you usually don't find anywhere else. And as always, if you like this type of content, remember to hit like, hit subscribe, and hopefully I'll see you in one of our next videos. Ciao, ciao.